So, this is the title of these lectures, and a brief outline of what we will discuss. I will start from an introduction of about neutrinos in the Standard Model. And beyond. So, in particular, we are interested in introduce masses for neutrinos. And as a consequence, we will find that neutrinos also are mixed, so mixing. And we'll discuss a bit about interactions of neutrinos. Then, once we have seen that the massive neutrino implies mixing, we will study neutrino oscillations. Neutrino oscillations are the main tool to measure, characterize the neutrino physics, neutrino parameters. We will see in the beginning vacuum oscillations, and then matter oscillations, both in constant density, for constant matter density, and varying matter density. And then, let's say, we'll make an overview of neutrino phenomenology. In particular, we'll see what are the sources of neutrinos. There is a huge type of neutrino sources. Then we will see how experiments study neutrino oscillations and use them to measure neutrino parameters. And so we will see how combine all available data from oscillations to measure neutrino parameters. So let's say we will see how global analysis allow us to measure neutrino parameters, and in the end, we will see how cosmology and astrophysics contributes to the characterization of neutrino properties. So we will start with neutrino in Standard Model, and as you know, neutrinos are massless particles in Standard Models. The Standard Model is a gauge theory based on the SU3 times SU2 times U1 gauge group, where the SU3 refers to color, SU2 left to the weak isospin, and U1 to the hypercharge. And since we are interested in neutrinos, so in weak interactions, we will not discuss SU3, but concentrate only on the SU2 times U1 subgroup. The cross product means that these groups commute, so they don't see each other, so we can forget about colors for neutrinos. So here the two key words are left and hypercharge. And let's start with left SU2 subgroup. What does this mean? This means that the building blocks of the standard model, consider for instance just one family. We will start with electron, neutrino, U quark, and D quark. These are leptons and quarks in the first family. And with E or nu E, I mean the spinor psi E, or the spinor for the neutrino, and so on. Now, we can consider for these fields the left and the right part. So, for instance, in general, for a spinor, we can write psi as psi L plus psi R, where these two parts are the eigenstates of chirality, meaning the gamma 5 matrix. So gamma 5, psi R is equal to plus psi R, and gamma 5 psi L is equal to minus psi L. But just for let's try to remember what these gamma matrices are. We have two main representations for gamma matrices. One is the Dirac-Pauli representation, where gamma 0 is diagonal and gamma 5 is not diagonal. So in the Dirac-Pauli representation, we have that gamma 0 is equal to 1 minus 1, 0, 0. Gamma I is 0, sigma I minus sigma I. And gamma 5, that is I, gamma 0, gamma 1, gamma 2, gamma 3, is 0, 1, 1, 0. Okay, but we will not use this representation, because to discuss neutrinos, it is better to use the Weil representation. So in the Weil representation, the role of gamma 0 and gamma 5 is interchanged. So the gamma 0 is not diagonal. By the way, here, these blocks are 2 times 2 matrices. So because the gammas are 4-dimensional. Gamma I, with I equal to 1, 2, 3, are the same. And gamma 5 is 1, 0, 0, minus 1. So this is the representation we will use. And also remember that the gamma 5 anti-commute with all gammas. Now, if we go back to the R and left part of a Dirac spinor and define psi L, psi R, as 1 plus gamma 5 divided by 2 psi, let's see what this is. So this part cancelled, and so we have 1, 0, 0, 0. Imagine that the spinor is chi phi. You end up with two-dimensional vector here. So the R part of the spinor in the Weyl representation contains upper components, while the lower one, the left one, sorry, gamma 5 upper or lower index is the same, like gamma 0, while gamma I, if you put the indices down, you get a minus. So here, when we make the difference, this one disappears, this gets plus, so you get 0 up and the lower components. So the Weyl representation is much more useful because you can easily see that the right-handed spinor has upper components and the left-handed spinor lower component. Remember that helicity and chirality is defined from the eigenvectors of gamma 5, are the same thing only for massless particle, because for when mass is different from 0, they are different. But I will say left-handed to mean the left part. Now, let's go back to the SU2 left. SU2 left means that the building block of the theory, of the standard model, will be the left part of the particles, so quarks and leptons, on one side, and then the right part. For the electron, we have ER, morning, and also for the quark, we have the right part. While, sorry, this is electron neutrinos, but for one family, we can also forget about the index. Neutrinos, from the beginning, do not have the, so in this case, neutrino, only one neutrino, does not have the right part. Now we put the leptons in a doublet, the left part of the leptons, so nu EL, EL, and also, let's say, for quarks, the left part, UL, DL, in a doublet. Now we see what doublet means. And you see the right part of the electron is a singlet, and also singlets are the right part of the U quark and the quark. What means doublet? SU2 is the symmetry group we are considering, and this doublet, under a transformation of SU2, goes into UL. U is a matrix of SU2 and is the fundamental representation, two-dimensional fundamental representation of SU2. Obviously irreducible representations, because this is what we require for the fields. They belong to representations, irreducible representation of the symmetry group of the theory. If you instead consider, for instance, the right part of the electron, under SU2, it goes to itself, so it does not change. And this is true also for the quarks. Now, when we write the Lagrangian for a theory, first of all, we require that we have a scalar and a Lorentz transformation. So, for instance, start from a Dirac field, a free Dirac field. So the Lagrangian is psi bar I d slash minus m psi. Okay, so this is just for one particle, for instance, for the electron. Here we can use the decomposition of psi, the spinor, into two parts. And this Lagrangian takes the form psi L I d slash, okay, let's divide in two parts. Psi L plus psi R E d slash psi R minus m. I write directly the result. So, in the part that depends on that contains a gamma mu inside, left is the structure. Also here, right, while in the term proportional to the mass of the field, for instance, an electron, a free electron, we have this structure, psi bar R, psi L, and the Hermitian conjugate. This is a consequence of the fact, for instance, let's take this term here, psi bar R, psi L. Psi L is 1 minus gamma 5 divided by 2 psi, and psi bar L is the 1 plus gamma 5 divided by 2 psi. This would be psi bar, psi R, complex conjugate gamma 0. Now, the gamma 5 is real, so the dagger does nothing here. So this is psi bar 1 plus gamma 5 divided by 2 gamma 0 1 minus gamma 5 psi. And when you put the gamma 0 on the left, thanks to the anti-commutation, this gets a minus, and when you do 1 minus gamma 5 squared, this is 1 plus, okay, so what is there? So 1 minus gamma 5, this, what is this, 0? What I'm doing. So, okay, so you get twice minus twice gamma 5, okay, and you get something that is different from 0. When you study instead a term like this, or a term like this one, you will get something that is 1 minus gamma 5 times 1 plus gamma 5, and this is 1 minus gamma 5 squared, that is 0. So if you expand this psi bar psi product, only these two terms will survive. Here there is a gamma mu inside, and this left survives. Now, I say left because this is the lower index, but actually it is easier to see that this is a right particle. So if you compute psi bar L will have only upper components. Try to do it yourself. While psi bar R will have lower components. Okay, now let's go back to the SU2 doublet. If you have questions, please ask and interrupt me. Now, if we try to write something that is an SU2 singlet, like this, this is by definition, remember that L has a neutrino up and the electron down. So nu E left, electron left. And so you see immediately that this is 0, because you have psi bar left, psi left, E bar left, E left. So this is 0. This means that in the standard model, if we require, okay, this is a singlet under SU2, because under SU2, this goes in U, L, and this goes in L bar, U dagger. But this is 1, because U is a unitary matrix, so this is equal to L bar L. But this is 0. So if we require that our Lagrangian is invariant under the group SU2, left, I cancel, we cannot have a mass term, like for a free electron, for instance. But we need to, if we want for the electron E bar left, ER plus, let's say, minus M, E bar right, E left, we need some other ingredient. Because remember, we want scalar under Lorentz symmetry and also a scalar under SU2 symmetry. Let's see the other part now. We have, so SU2 left cross U1 hypercharge. The hypercharge is defined as the difference between the charge of a particle and the third component of the isospin. This is the Klein-Nishijima, the Nishijima-Gell-Mann relation. Now let's see for the doublet and the singlets what is the hypercharge. For the neutrino, we have the charge is 0, and the third component of the isospin is 1/2, plus 1/2, minus 1/2 for the electron. So we get minus 1/2. For the electron, we have the hypercharge equal to the charge, now this is minus 1, minus 1/2. So this is again minus 1/2. So in this doublet, the hypercharge is equal to minus 1/2. Let's see instead for the the right part of the electron. The hypercharge is, the charge is -1. This is a singlet under SU2. So the I3 is equal to 0. So -1. You see that these terms do not respect the SU2 symmetry, because this is in a doublet. So isospin equal to 1/2. This is a singlet. We need in all, we need a singlet under SU2. So these terms cannot appear directly into the Lagrangian. But also, if you consider the hypercharge, this is -1. The bar here contains a complex conjugated, so this is +1/2. So -1 plus 1/2 is not 0. So this is not good, both from the point of view of the SU2 symmetry and from the point of view of the U1 symmetry. We need to combine these terms with something that compensate for the hypercharge and for the weak isospin. And this is the Higgs field. Also, remember that the Lagrangian, to have a renormalizable theory, must have dimension 4 in mass, and a spinor has dimension 3 divided by 2. So 3/2 is 3, so we miss one other dimension, and the scalar field has dimension 1. So we get a Lagrangian with dimension 4. How to, okay, we need something that I said is a singlet under SU2. So I can try something like this. This, to be a singlet under SU2, must be something like this. So this is a row, this is a column. This gets a U dagger under the symmetry. This gets a U dagger U is unit, and so this is a singlet under SU2. And this is a singlet under SU2 by construction, by definition. So this scalar field must be a doublet of SU2. The hypercharge, we said that the lepton doublet has hypercharge -1/2, so L bar has +1/2. The right part has -1, because we have charge minus I3, that is 0. So this must have hypercharge 1/2. So if we build this product here, we have dimension 4, and this is good for the renormalizability of the theory. Singlet under SU2, and singlet, so weak hypercharge equal to 0 for U1. Obviously, we need this term plus the Hermitian conjugate. So the psi bar, psi dagger, L, and sorry, E, let me write first, ER bar, psi dagger, L. This is again you see a singlet under SU2, and the hypercharge is equal to 0. So this is the way. Sorry.
Is the condition that hypercharge equal to 0 identical to asking that the singlet under?
Yes, because when you make an U1 transformation, you multiply by aphasis, okay? And if the hypercharge is equal to 0, you get e to the I0, so 1. Okay. Now, what happened with the Higgs mechanism? The Higgs mechanism, so in the Lagrangian, this, okay, let's see first what is exactly this doublet. This doublet must have, I said, hypercharge equal to 1/2. So, if we consider, let's say, Q equal to y plus I3, now this is 1/2. So in the upper part here, we have I3 equal to 1/2. 1/2 plus 1/2 is 1, so the charge is 1. We have a charged scalar field, and down we have 1/2 minus 1/2, so 0, and this is a neutral scalar field. The Higgs field gets also a potential in the Lagrangian, and because of this potential, the mechanism of the breaking, the spontaneous breaking of the symmetry makes this field acquire a VEV in the vacuum. So the expectation value of this field is not 0. This is V divided by 2, 0. Okay, let's write like this. 1 square root of 2 V plus the Higgs field. In a gauge that is called the unitary gauge, near the minimum, the Higgs can be expanded as a constant term plus the Higgs field. Now, this part here, in the Lagrangian, the Yukawa part of the Lagrangian, will give the interaction of the Higgs. But we want to see what happened only by considering the minimum, so the vacuum expectation value of the field. It is this one. And let's see what happens with these terms here. So let's consider, for instance, L bar phi ER. This will be L bar V over square root of 2, 0. Okay, let's write explicitly. So nu EL bar, 0, 1, ER. So V divided square root of 2. And when you multiply this one, only the electron part survives. So you get exactly one of the two terms that you need, this one. And if you consider ER bar psi dagger L, this is E bar R, V square root of 2, this is real, so this is 0, 1, nu EL, now the EL survives, so V square root of 2, E bar R, EL. So the spontaneous breaking of the symmetry simplifies these two terms and give us exactly the terms we wanted, because these are the terms, where is, I cancel, that represent the mass for the electron. But they come from something that respects the symmetry of the standard model. And we can extend this part to the quarks. But the quarks, now if you see, we were able to give mass to the lower component of the SU2 doublet. The neutrino do not have masses in the standard model from the beginning. But if you consider the quark doublet, with this, with terms like this one, we can give mass to the D, the quark D. We have QL bar phi. Instead of E, we have dr plus dr bar phi dagger QL. And this is, after the, with the Higgs mechanism, V square root of 2 dr bar dl plus dl bar dr. So we are half the way, because we have the mass for the electron, the down quark, we miss still the U quark. Now, the SU2 group SU2 has this nice property. Consider, we said that the U, so the matrices itself, are an irreducible two-dimensional representation of the group. But also we can consider U star, so the complex conjugate. This is also a two-dimensional irreducible representation of the group. But for SU2, we have that these two representations are equivalent. So there is a matrix connecting the two representations. This is true for SU2. This is not true for SUN with n, 3, 4, etc. Thanks to this property, okay, by the way, this matrix is I sigma 2. I sigma 2 is, because sigma 2 is minus I, so this is the Levi-Civita symbol in two dimension, epsilon ij. And we can consider something that is related to the Higgs field. We call it phi tilde, that is this C phi star, and under the SU2 symmetry, this goes in C U star phi star, and with this matrix here, C, you can prove that C U star is equal to U C. So this is U C phi star, so U phi tilde. So we can build another field that transforms like the Higgs field, so with the fundamental representation. But if you try to explicitly write what this field is, so phi star, this is phi minus phi 0. So this is phi 0 minus phi minus. But with the Higgs mechanism, spontaneous breaking of the symmetry, this will go to V divided square root of 2, 1, 0. So the upper component. So if we consider Q bar L phi tilde UR plus U bar R phi tilde dagger QL, since now the Higgs mechanism will give this 1, 0 instead of 0, 1, you get the mass for the upper component of the doublet. So V square root of 2 U bar d UL plus UL bar UR. And this is how, for one generation, the matter field gets masses in the standard model. And since we started from the beginning only with the left part of the neutrino, we don't have a corresponding term for the neutrino masses. But as we will see in the following, if we introduce also for the neutrino the right part, with the same structure, we could get a mass like this for the neutrino. Elliot, maybe we can stop. Okay, let's make a 10, 15 minutes break. Thank you. Okay. By the way, I wanted to say that in the end, I will left you I will leave my notes, and if I jump somewhere in the lecture, you will find more precise formulas. And so we were at this point one generation, and we wrote that let's say the mass terms for the fermions in our theory were, let's say, minus V over square root of 2. Then let's put some coefficients, the Yukawa couplings, they are called, for instance, for an Fe, L bar phi ER plus ER bar phi dagger L plus FD for the down quark, the same thing, but with L change into QL phi dr plus the Hermitian conjugate plus FU Q bar L phi tilde UR plus Hermitian conjugate. Okay, so this is the Yukawa part of the Lagrangian, and after the breaking of the symmetry, this goes into V minus V square root of 2 Fe E bar left E right plus E bar right E left plus Fd D bar right D left plus d bar left, d right, plus f u bar right, u left, plus u bar left, u right, that we can write v square root of 2 fe e bar e plus fu u bar u plus ft d bar d. Since psi bar psi is psi bar right, psi bar left, plus psi bar left, psi bar right. So these are equal. Now you see that the masses of the fermions are proportional to V and proportional to these complex coefficients in general that are the Yukawa couplings. And now we want to extend this discussion to three generations. So we need to make the notation a bit more complete, able to describe three generations. And so the most straightforward way to do this is to define Li like, let's say, nu I left and Li with I that is electron, muon, or tau, and also, let me see, I want to follow the same notation. I define the Ri, the right component is, let's say, R1 is ER, yes, R2 is mu R, R3 is tau R. So the charged leptons have the right-handed part, neutrinos no, they don't have. And for quarks, we have QL, and we put an index I, with QL1 up down quark, QL2 are C, sorry, CS obviously, and 3 QL3 top, bottom, left. And all the right, so we have, let's say, URI, the right part for the up UC top, and the DRI for the lower component, so DR, SR, bottom R. And try to generalize the Lagrangian. So here we must add an index here, another index here, and obviously these couplings they becomes a matrix. So we have the Yukawa part of the Lagrangian is now minus f Lij, Li phi, I call this R, Rj, plus L bar, sorry, plus rj bar phi dagger l ij plus minus, let's call this f u ij. So we have here the tilde, so q li bar phi tilde u r I plus Hermitian conjugate plus f d ij q li bar phi, and here we have down rj plus Hermitian conjugate. So the structure is exactly the same, but now we have two different indices here, and this, that was a coefficient, is now a matrix. And there is no reason why this should be a diagonal matrix. This could be, these three matrices can be complex, arbitrary matrices, since we respect, in this way, the initial symmetry, gauge symmetry. Then, when after the breaking of the symmetry, we should be able to write something similar to this one. And to do so, it is better to introduce another notation still. We now define the lepton vector E mu tau left, and the right part ER mu r tau r, and for the quarks the upper left UL CL TL, and lower, let's call that D, Q, okay, before Q right up, UR CR TR, but also QDL, so DL SL BL, and QDR DR SR BR. And with this definition, the same Yukawa matrix here, after the symmetry breaking, is now minus V divided square root of 2. And we have these matrices here, F, I, J, and then L, Li, bar, L, R, J, plus Hermitian conjugate, plus F, U, I, J, the upper Q, upper L, I, bar, Q, R, J, U, upper, plus Hermitian conjugate, plus F down ij q bar d l I q r j d plus Hermitian conjugate. So if you compare this term here with that one, it is the same thing, but you allow for non-diagonal terms. depending on these general matrices. So this is the extension of the Yukawa terms that we introduced to respect the symmetry, but to give masses to the fermions to 3 generations. Now, let me cancel. Okay. Up. The mass eigenstates we want to find. So we need to diagonalize some way this F matrices. Now we don't have any mass matrices for the neutrinos because we are considering neutrinos as purely left-handed. Now let's, for instance, consider the up quarks, the up 3 quarks, so this part here, okay? It can be shown that we can diagonalize, so this is U. So Fu is this matrix here, okay? It can be diagonalized by what is called a bi-unitary transformation. So we find, it is possible to find 2 matrices so that this is diagonal. So there is no, in general, this is not diagonalizable by means of only 1 matrices, but you can find 2 matrices to do that. And if you consider the Lagrangian term minus v divided square root of 2, q bar u l f u q r so this is qr, what is, maybe this is wrong, q bar down u. Okay, you can insert twice these 2 matrices here. So this is minus v divided square root of 2 q bar u left. Then we have w up left dagger fu times another wr dagger q up r. So just put the identity here twice, once with the left, wu left, sorry, there are many indices, but actually these are 2 matrices. And we need to put the indices to do the same thing 3 times. Now, you see that this is exactly the diagonal matrices. So you have minus v divided square root of 2 q u l w u l, then the f u diagonal, and the w up right dagger q r up. Okay, now we can define, let's write here, this is diagonal. This is what we wanted. We redefined these two vectors as, for instance, Q R up dagger Q R U. We can call it Q R U, the zero, where we put the zero, Q 0 R. Okay, and Q R U is W U Q U 0 R. So we redefine this here so that we have minus V divided square root of 2 Q 0 R U diagonal matrix, and also here the Q 0 left U W left U dagger Q left U, and so Q0 left bar U. So this is a bit confusing, I know, but we have found through this unitary matrix, one for the left part and one for the right part, the mass eigenstates, okay, for the up quark. With a lot of indices, we can do the same for the down quarks. We have two more matrices with a D here, left and right, and also for leptons, for the electron, muon and tau, with two more W leptons, let's say, right? But I will not write that. Just want to show that what happens is that if we consider the current, the charge current, the weak charge current, the weak charge current for quarks, J mu, is twice U bar left gamma mu dl plus CL bar gamma mu S left plus top left gamma mu B left. Okay, so as we have seen, where there is a gamma mu, only left terms survive. And so in our notation, this is twice Q U L bar gamma mu Q D left. Every quark is coupled to the down, up with down, and there is a charge 1 transition. So this is charge current. And by the definition of the mass eigenstates, this is 2 Q0 U left bar W U dagger left gamma mu W L D Q0 left D, that we can write as 2 Q0 left up gamma mu. These are matrices for SU2 transformation. So while this is for Lorentz spinors, so I can move this matrix here, W up left dagger W L D Q0 left D, and I call this matrix the U. This is the product of two unitary matrices, so itself is unitary, and this is the CKM matrix. So, from the general property that the Yukawa couplings need not to be diagonal, with a lot of indices, I write some quite complicated things on the board, but you get simply that when you consider the charge current, there is a mixing matrix for quarks. Okay, this is the result, and okay, we can do. If we try to do the same thing for the leptons, there is an asymmetry because you see here we have up component and down component, and we know that neutrinos are different. So let's see what for the leptons what happens. For leptons, I could write for the F, okay, I cancel, for FL, the matrix that appears for the L leptons, for the electron, mu, and tau, a biunitary transformation, or L, put an L here, L is for lepton, that is diagonal, FL diagonal. Okay. No corresponding transformation for neutrinos because the mass term is absent for the beginning for neutrinos. Now, if you consider the, let's say, the current, J mu for leptons, the weak charge current, you have twice nu L gamma mu L, and now again we can, sorry, I missed, okay, no, that's right. So we can define the mass eigenstate for the leptons as for quarks, L dagger LL, and also for the right part, W R L dagger LR. And here I can insert twice the identity. So twice nu bar L gamma mu. Since I need so WL dagger LL. This is L0 L, but there is no corresponding matrix here on the neutrinos. So I can simply redefine nu L as nu L dagger nu L. Just a redefinition of the neutrino fields. I'm free to do that. And I call this now as the flavor eigenstates of neutrino. These are coupled directly to the mass eigenstates for the leptons. So the fact that there is this asymmetry allows one to preserve the structure of the current by considering the mass eigenstates coupled to the flavor eigenstates of neutrinos. They can be redefined through this transformation. Okay? And this is how neutrinos appear in the Standard Model. So, without masses, there is no mixing for neutrinos. But we saw in our previous discussion that, in principle, since nowadays we know that neutrinos have masses, because in 2015 there were 2 Nobel Prizes for neutrino physics to McDonald and Kajita, because they found evidence for neutrino oscillations. And as we will see, neutrino oscillations implies that neutrino possess masses. So we should now try to extend the standard model so that neutrino masses are included. And the first thing that we can do is to treat neutrino exactly as we have done for quarks. So to introduce the right-handed components for neutrinos. And the procedure, okay, would be the same, I canceled, but would be the same exactly as we introduce the mass terms for the upper quark components with the phi tilde. We would do the same for neutrinos. And also we would get here another 2 matrices, okay, without writing again all the Lagrangian terms, because we extend what we have done simply by considering the phi tilde terms for neutrinos. And in this case, the charge current, weak charge current, would change so we would start again from this expression here, J mu L W C, so the charge weak current leptonic, and this would be 2 nu bar L gamma mu L left. Let's call the matrix that diagonal corresponding to neutrinos. We would have a new matrix F, neutrinos, that we could diagonalize by a bi-unitary transformation, again with W exactly like this one, but imagine here to put neutrinos. And instead of calling W, we can call it V, so left, neutrinos dagger, V are neutrinos. Now neutrinos have right-handed fields, and this is F nu diagonal. So where is the, also for neutrinos we could write this new with V. Okay. So let's define nu 0 L equal to V L left dagger nu L, and insert twice the identity here, as we have done for quarks, for the up quark. And so we have twice nu bar 0 L W nu L dagger gamma mu, so V, not W, W L lepton L0 L. So insert twice the identity, then use the relation between mass eigenstate and flavor eigenstates, you get 2 matrices, but here we do something different. This is nu 0 L bar V L nu dagger W L L gamma mu L 0 L, and we call this matrix here U dagger, and sometimes PNMS. These are Pontecorvo, Naki, Makata, Saka. I don't remember exactly the name, sorry, but this is the mixing matrix for neutrinos. And we can do one more passage here. So if you define nu L, the flavor eigenstate, now has W L dagger nu L. So also here we do a redefinition of neutrino fields. This is W L L dagger. Then we insert V nu L V nu L dagger, the identity. This is exactly U nu L0, because this is the mass eigenstate for neutrino, this is the mixing matrix for neutrinos, and so the charge current, let's write it again, can be written as nu bar L gamma mu L0L. This is the final result, where the nu L are related to the mass eigenstate by the mixing matrix, and flavor eigenstates, neutrino flavor eigenstates, are coupled to mass lepton eigenstates that typically we write without the zero. So we followed a completely analogous path to the one we have followed for quarks. And now we have that a matrix, a unitary matrix, describing mixing of neutrino appeared in the charge current, weak charge current, while the mass terms for neutrinos, once we diagonalize the F nu matrix, will have the same form as for electrons, muons, and taus. Okay? So, if you, in the simple extensions of the standard model, introduce the right components for neutrino, and this is called a Dirac mass term for neutrinos, you get mixing when you write the flavor eigenstates so that they are coupled to leptons in the weak charge current. Okay, so this is the first simple possible extension of the standard model. But there is a problem. It's not a mathematical problem from the point of view of the consistency of the theory. We saw that the fermion masses are proportional to the vacuum expectation value of the Higgs field, V, and to the Yukawa couplings. Okay, and this is true for all fermions. But you have for lepton, for instance, for the electron, 0.5 MeV mass. For the quarks, okay, masses are much greater, can be GeV or more. For neutrinos, we know that masses are of the order of 0.1 electron volt. So why the Yukawa coupling, if neutrino masses are of Dirac type, why they are so small? Why the Yukawa couplings related to neutrinos are so much smaller than the other? And this is part of the hierarchy problem. But there is another way to introduce neutrino masses in the theory. So this, what we have done in this minimal extension of the standard model was to introduce in a completely analogous way to what we have done for charged leptons and quarks, the right-handed component for neutrinos, and so that's why they are called Dirac masses. But there is another way to introduce neutrino masses in the theory. And we now discuss the case of Majorana masses. So once again, I want to stress that if you want to properly write the Lagrangian for three families, you get a lot of indices, okay? And so things appears to be a bit confusing. But actually, the meaning of what we have done is very simple. When we introduce more families, the Yukawa couplings begin matrices. We can diagonalize these matrices, but is the diagonalization a bit strange, by unitary diagonalization with two matrices. And when you consider the current, when you define the mass eigenstates, both for quarks or for Dirac neutrinos with masses, you get a mixing matrix for the charge current. Okay. Now, neutrinos are neutral fermions, and one possibility is that they are their own antiparticles. So, remember that if we have defined the left part of a spinor. Let's put a left here, because when the lower components correspond to left particle, and upper component, let's go chi r, corresponds to right-handed field. Now, consider the possibility that neutrinos are their own antiparticles. The conjugated field to a spinor, a Dirac spinor, is defined as in this way. So you have a matrix that is I, gamma 2, gamma 0 times psi bar transpose. Now, psi bar would be a row column. You need a transpose to get, this would be a row, sorry, and the transpose is a column. So you have I, gamma 2, gamma 0, and then psi dagger gamma 0 transposed. So I, gamma 2, gamma 0, the transpose of gamma 0 is still gamma 0, and psi dagger, so psi star transpose, so that's all, and this is 1, so I gamma 2 psi star. So the complex conjugate of the spinor is this one, or explicitly depends on the complex conjugate and of the gamma 2 matrix. If we write explicitly what gamma 2 is, so psi star, let's say phi star chi star. Okay, maybe not now. This is the charge conjugated field. Now, imagine 5 minutes. Okay, time so quick. Take the left part. The left part is this one. So I gamma 2 psi left bar, so let's say star here. So I 0 sigma 2 minus sigma 2 0 and 0 chi star left. So I, this is not 0 and minus sigma 2 chi left star. So we discover that the complex conjugated field of psi left is right. Make a mistake. Sorry, this is up sigma 2 psi left star. I wanted to discover, and I finally discovered, that the left psi left conjugated is right. So I go from lower to upper components. And if I take the right, I 0 sigma 2 minus sigma 2 0, so chi r star 0. Now I get 0 up and minus sigma 2 chi r star. So the complex conjugated of a right spinor is left. Okay? Now, if we want, and this is one thing, if we hypothesize that the neutrino is a Majorana particle, so it must be its own antiparticle. It is clear, for what we have said, that it should be of the kind, so this is a condition that eliminates 2 degrees of freedom. Spinor has 4 components, so 2 Weil spinors, upper, lower, chi and phi I called. But if this condition makes possible to express Majorana spinor in terms only of the left component, because when I take the charge conjugation, this terms gives the second one, and the second one this gives the first one. Okay, and tomorrow we will see that since we need some terms of the kind psi bar L, psi L in the end, we could use these 2 fields to build a new Lagrangian term for neutrino masses in the case of Majorana particles. But maybe we stop here and we will continue tomorrow. Okay.